Okay, let's just check that that is working. Excellent. So, wake up my computer. My name is Andre. I'm an engineer working for a company called Digital Asset. We happen to be involved in building a replacement for the share registry and settlement system for the ASX. I'm not actually here to talk about that project here this afternoon, but I do want to talk about the smart contract language and the platform and the architecture that we're using behind this, because I happen to think it's really quite cool and quite interesting. But before I do, I want to actually leave IT for a moment and talk a little bit about legal contracts. Especially in the financial world, legal contracts are the bread and butter. Almost everything you're dealing with is a legal contract. So if we're going to deal with contractual workflows, we need to think about what the requirements are that come out of our problem domain. So the first most fundamental principle, we have multiple parties. If you don't have multiple parties, you don't have a contract. These parties also have a need to somehow establish some ground rules to collaborate. What they're trying to do is they're trying to establish trust. This is like building any relationship. You communicate up front, set expectations, and a contract is really just formalizing the expectations of what is going to happen as a part of this relationship, even if the relationship is only for the few minutes it takes to buy an apple, all the way through to decades worth of joint partnership or whatever. Now, the law requires that for it to be a contract, you have to have something called certainty. What that means is that everything that is going to be the result of a contract has to be foreseeable up front. You can't leave non-determinism or some sort of random vagueness, anything down there. When you sign the contract, you need to know what it is that the two or the N of you are agreeing to do. You can't contract to agree in the future. The contract is the agreement. And as a part of that, we actually have to have this idea of offering and acceptance. Someone has to offer to form a relationship, and the other one has to accept that relationship. Without these two things, you do not have a contract. This is part of contract law. And then the contract itself, what's in the body of the contract? Well, first of all, you have certain obligations. If I contract with you, we may actually obligate me to provide you with $20. That may be an obligation that I have. On the other side, it may also grant rights. In exchange for that $20, I may have the right to use your lawnmower. I don't have the right to use your lawnmower without this contract, but we sign a contract or handshake a contract, I give you $20, and now I have the right to use your lawnmower. So there's this concept of obligations and rights. Finally, there is this idea of privity of contract, which is that if we have a contract, it can't involve other people who haven't actually agreed to join. It has to be voluntary. And finally, as a practical matter, especially in a highly regulated market like a financial market, you have a lot of issues around privacy and around monitoring. So we're going to have to meet that. There are a couple of other technical requirements, but they don't come into the technical influence, so I'm not going to talk about them. So, what are the technical requirements of an architecture to satisfy these requirements? So first of all, if we have multiple autonomous parties, we are going to have a distributed consensus problem. So we just have to face that up front. If we have a need to establish trust, then we need a way to independently validate the various operations that are being performed. So we're going to automate a contract we need the ability for each party to that contract to independently, without reference to the other party, verify that the operations that have been happened on that contract have actually been done properly. Certainty means that our operation has to be deterministic. We can't bring in random state from outside of the contract. Offering acceptance imposes an obligation on us to find a way to model consent. Because we have to have some way of consenting to a contract, or we can't form it. Similarly, we need some concept of delegation. In the contract I described earlier, we have to have some way to describe the idea that you have delegated to me the ability to use your lawnmower without further reference to you under that contract, under that pretend contract that we described. We also similarly need some idea of obligation. Under what circumstances does a party have to provide consent to actually be able to do, and forbid situations where we might actually perform an operation without the proper consent of a third party or another party. And so we need a model of that within our language. Finally, we're going to need some provision for secrecy in our architecture. And we're also going to need some way to guarantee that parties will be notified of the appropriate events that occur with respect to the privacy. So ultimately, we end up needing a distributed multi-party system. It needs to cross autonomous trust boundaries. It needs to support deterministic evolution of a consensus of belief. That evolution needs to be independently verifiable or validatable. It needs to be supported by formal models of consent, delegation, and obligation. We need to do all of that while guaranteeing privacy and guaranteeing notification. Oh, and as well as that, if you're dealing with large financial infrastructure projects, you also need to scale to billions of contracts, and you need to scale to millions of contract events per minute. So let's quickly go through the architecture that we derive from these requirements. So we have a distributed multi-party system. We have some sort of shared state, or at least some shared understanding of state. We have to be deterministic, which means we have to have a shared function that defines what a valid evolution or change to that state would be. This is what makes it particularly appropriate for a functional programming conference, because this is a pure function of state and command. So we end up with something that looks an awful lot like a CQRS system. Once we split that evaluation function into a function from command to a stream of contract events, and then define a state update function that is a fold over those events. So this is the starting point. You can do an awful lot with this architecture. A lot of people have. I know that we've had this architecture presented to YOW on previous years. So this is the starting point for my talking here. First of all, add trust boundaries. We have multiple parties reading the event stream, and they need to be isolated from each other because they don't necessarily trust each other sufficiently to be able to rely on the other party to get everything right. Just a reliance on the technical requirement is sometimes enough. Validation. Each party needs to be able to validate that the operation, the state update, was done correctly. So here we pass the command back with the event stream. So each bundle of events is actually passed back as a tuple containing the command and the resulting events, so that you can independently take that tuple, run the shared evaluation functions against that state, and verify that that actually function was evaluated correctly. For consent, we just add the idea that each command actually carries an authorization from a given party. And then we model delegation by storing those consents in the state. So state now actually carries within it authorization from prior commands, prior options, including things such as I offer. That offer is a command. That command, that when we actually resolve that, we end up with state that carries my authorization to carry forward to an accept. So when you come to accept, you can add your authorization to it, but you don't have to coordinate with me in order to actually complete that contract formation. With privity, we add a constraint that that we can't actually manufacture authorization out of thin air. You must either obtain the authorization from the command, or you must obtain the authorization from the pre-existing state. You just can't invent authorization. Finally, in preparation for solving some of the privacy problems, we run the entire evaluation function on the client. There's no need to run it on a central server because it's deterministic, it's pre-degreed, and there's no actual, because of the determinism, there isn't actually anything different between running it on one node versus another. And every node, these are going to be validated anyway. So we end up with this architecture for a centralized smart contract system. The difficulty we have here is that we still have a centralized state. However, I hinted before, we actually have a situation where that state's not necessary. We ran all of the evaluation on the state locally on the individual parties, and then we revalidate that state evaluation on each of the subsequent parties that are stakeholders to the system. As a result of which the state on the central server is actually no longer relevant. There's no need to run it in a central place. You can run it out on the edges of your distributed system in a peer-to-peer fashion. And as a consequence of that, these states only need to be consistent. They don't need to be equivalent. I can know things that represent my relationship, my contracts with Jed, and neither of us have to share that information with Manuel, who I might have separate contracts with. As long as every contract is actually shared, the details are shared with those parties that need to be able to validate it, there's no need for any central state. Finally, for notifications, if we actually fold into the event the list of people who have to be able to observe that event, so that that actually becomes a part of the nature of an event, then we can guarantee that when we run that evaluation function that it's impossible to leave someone off. Because by definition, if it was a valid function, you computed the observers correctly. And so the list of observers, the list of parties who must be able to see it must actually be correct. So this is the resulting architecture. No centralized state, it's peer-to-peer. But it still has that core CQRS event sourcing style. So you'll find the normal sort of programming styles that you're used to with that actually fit quite nicely here. Okay, so let's take a look at the language. So DAML. DAML is the language that we use at DA. It's now open source, so it can be used by anyone, to define that evaluation function. It is a dialect of Haskell. So with only a few small syntactic changes, we have access to all your favorite GHC extensions, most of them anyway. We can define data, and we can derive type classes from it. In this case, I'm going to build a market for trading collectible card games. Seemed like a reasonable small project. So here's a description of a card. It's been issued by a publisher, and it has a card text. We'll abstract away from that. So DAML extends Haskell with this concept of a template. This is a specific data. This is a data structure that defines a number of type classes implicitly that allow it to interact with the ledger, that allow it to participate as part of commands, as part of transactions. In this case, it defines a record, and it defines the necessary authorization necessary to both create this record, this contract. It also is the authorization that contract carries when it actually performs operations. So here we have a scenario. We create a party. We create a handful of parties, and then we attempt to create the card, but Alice does that on her own. The result of that, when we run this, is that we get a scenario execution failure due to missing authorization. There were 4 parties to that contract, and only one of them authorized it. And so we get notified that we were missing authorization. So the semantics of the language will prevent you from, protect privity of contract, and will prevent you from creating a contract without a proper authorization. So create a marketplace. Again, a couple of parties, the manager of the marketplace and the auditor who regulates it and makes sure that everything is done properly. Again, because there are 2 signatories to the marketplace, you can't create that on your own. There has to be an offer and acceptance to create the contract between the 2 parties. So here we have another contract template that only has 1 signatory. Because it only has 1 signatory, this is something that can be created unilaterally. The manager can create this contract without reference to any other party, put it on the ledger, and make it available to the auditor party to choose to accept. So this controller function choice here is a function of no arguments that can be triggered by the auditor, and as a consequence of that will create this marketplace with the authorization of the command and the authorization of the contract offer, and as a consequence of which we can create this marketplace. And so here we have an example where the manager submits the proposal, and the auditor then exercises the accept. And if we run that, we will see that the second transaction has actually run through in that way. So here we have the creation of the proposed market contract, and here we have the resulting creation of the marketplace by the auditor. Now, the important thing about DAML here is the fact that we can manage these workflows. The workflows are defined in terms of these choices. We are very much, the modeling language of DAML is an intentional language. The language is defined in terms of what can parties do. So when we create a contract, we don't generally create a contract thinking in terms of data. We create the contract thinking in terms of what can the various parties do? What are the rights? What are the obligations? What must they do? What can they do? In this particular case, this marketplace grants the manager the permission to invite a publisher to join the marketplace. So here the manager can invite the party, and we can add that to the publisher. Now, here, I will point out that there's no need for an offer and acceptance here, because the signatories to the marketplace are only still the manager and the auditor. The publishers are just informed of this. They are not actually obligated here. So we have a situation where we here are modeling the difference between merely being an observer of a contract and actually incurring an obligation as a consequence of this. And in this particular case, the publishers do not incur any obligation as a result of this contract, and we encode that directly here in the language. Oops, sorry. Here we are, just move on to delegate. So once the publishers have been added to the contract, we can actually delegate to them rights. So we can, the manager and here what we're doing is we're saying the manager and the auditor have agreed that these individuals who are publishers have the right to invite players. And we will manage those players. And so here we have this idea of the ability to have a choice where we add, the publisher passes in also a player, and we will add that player to the list of players. Now, one aspect of the DAML language is that it has a linear semantics by default. So every use of a contract invalidates that contract. We don't support any concept of mutable data on the ledger. If you want to update it, as we do with any FP program, we delete or we garbage collect the previous state, and we create a new contract in its place with the new data. There are some situations, however, where you want to grant a permanent right to perform some operation. And in that case, we do actually support this idea of non-consuming, of a non-consuming choice. In this case, this allows a publisher to create an offer to a player to accept a card. I'll skip past that one. The other thing that we can do here is encode the concept of delegation. Here what we have is a choice where the publisher is given the ability by the manager and the auditor to update the card text, to apply an errata to the card. Again, this means that at the point here where we actually have a choice that will consume this contract and create a new version of the card contract, these signatories, which includes the owner of the card, the player who owns the card, by being signatories to this contract, they grant permission to the manager and the manager, the auditor, and the publisher to jointly apply errata, which means that we can control exactly how that errata can be applied via this delegation. Because this delegation, the command comes in with a single publisher authorization, but the marketplace contract itself carries both the authorization of the manager and the auditor. And so we get those three come in together. So the DAML asset modeling language. It is a pure functional Haskell dialect. It has a formal operational semantics. It provides a technology-neutral ledger model. So DAML, the language itself only specifies that evaluation function. So it doesn't mandate anything on the actual consensus layer underneath. It runs on anything from Postgres through to your choice of a blockchain, depending on what your actual requirements are. The language also provides a model for privacy and disclosure. As you saw, authorization and consent, and completely deterministic evaluation. The consensus that we actually use in our platform is a distributed consensus by applying a total ordering on the commands. So as the commands come in order to be able to validate properly, all you need to know is what is the state that should be validated against. And if you know the total order over the commands, then a fold over the resulting events structures will actually provide you with that state. We like to model the right to act. So the DAML model is primarily about choices that are written in Haskell, but which they actually define what are the valid choices that individual parties can make that will evolve the state in an agreed manner through the workflow. It's not a CRUD system. This is something much more akin to a CQRS system or an event source system, but it's doing so with an intentional system of verbs, of actions, of rights, rather than of explicit state transformation. And so each contract on the ledger then represents formal proof that the signatories to that contract have actually authorized or have agreed that that fact can be relied upon. Formally, that would be described as a justified basis of belief. And that holds for the lifetime of that contract. So there are a number of resources. DAML, as I said, has been open sourced. We have our own deployment of Hugel that we've run over the DAML standard library, so that's available as a documentation source, as well as the standard SDK documentation. A series of blog posts that go into this a lot further, as well as a public Slack, and these slides and the associated code are available on my local GitHub repo. So, any questions?